The plan for this talk basically is to give an introduction to some new techniques we've been developing out at Curtin, and provide a bit of a case study of where these new techniques I think have been quite useful and added extra information that's really helped our understanding of geological processes. So I'll talk about some case studies from Western Australia, but I'm also going to broaden it out to some case studies from other places around the world, just for your interest. The background there is a zircon. Everyone loves zircon, everyone's favorite geochronometer, but I'm not really going to talk too much about that, so I thought I'd get in one nice picture of a zircon. All right. So hopefully you can see my second slide. Please shout at me if this doesn't work. Second slide is basically just an intro of what we're going to talk about. So what I'd like to do is very briefly outline how I think about geochronology and isotope geology, just as a kind of context for what we're going to look at in terms of the tools we're going to look at. Specifically, I'm going to give some case study examples of common lead isotopes and what they can be used for, and how we're using them in K-feldspar grains to help us understand crustal evolution. I'll talk in a bit more depth about apatite and samarium, neodymium, lutetium, hafnium, and uranium lead in apatite, and how that can be used to track a parcel of rocks through various time temperature points on its evolution. We'll also talk about biotite, rubidium, strontium. I think this is a particularly powerful tool and very relevant for understanding the age of fabrics, and I think particularly useful for linking geochronology or thermochronology into mapping. And then we'll also touch briefly on some lower temperature thermochronology and understand how that's important for landscape evolution, but also lower temperature geological processes. So if you like, this is a bit of a degustation. It's only going to be a flavor of these things. If you want to know more detail about it, please do get in touch with me. If you want to keep up to date with kind of what we're doing out at Curtin, we've got a Twitter feed, so that's something that you can join on if you're interested. Okay, so the way I think about isotope geology or geochronology is on a kind of a scale ranging from systems that are isotope tracers, where we have no daughter product produced, all the way through to geochronometers that we're pretty familiar with. So this would be our zircon, uranium, lead would be the classic example of this, where more or less all the information we get is about time, is about age. We've got systems in the middle here which maybe give us some information about time, but also give us some information about source signature. So apatite, rubidium, strontium is a good example of a source signature because it doesn't produce any radioactive decay of radiogenic strontium. So what we get is a source signature telling us about the fluids that formed this apatite, where they came from. Garnet, SMND, and biotite, rubidium, strontium are more towards the geochronometer end, in that they provide time information, but not necessarily as much source information, but some source information. So these schemes that are isotope tracers and geochronometers tend to be dealt with using an isochron technique. The isochron technique is basically we plot the amount of parent isotope against the amount of daughter isotope. So the more parent we have, through time, we're going to produce more daughter. The less parent we have, the less daughter we're going to produce. So therefore, over time, the slope of this line is going to change, and that's our time information, our age information. As this rotates, we can get age information, but also importantly on the ordinate axis here, on the y-axis where it intercepts, it's basically the initial ratio of the system, so that gives us source information. Is the fluids growing our garnet, for example, are they mantle-derived fluids, or are they more crustal-derived fluids? We can get that sort of information out of the initial ratio from this end of the diagram. With pure chronometers, because there is less of the initial information there, we tend to use more isotope-specific diagrams, like the beautiful inverse Terra-Wasserberg diagram. So they're more specific diagrams for pure chronometer systems. At the other end, we tend to just use weighted means because we're not seeing things changing with time. We're looking at a source signature. I guess another scale we can probably think about in if we look at the rubidium-strontium system, just for example, in biotite, biotite's so radiogenic, it plots very far up our isochron diagram, so we can essentially tie it to the composition of anything. We can tie it to the composition of the moon. We're more or less going to get the same answer because it plots so far up this end of the diagram. Apatite, on the other hand, as I mentioned, doesn't have very much ingrowth, essentially none, so it plots down at the other end of the diagram and tells us something about source composition. All right, so a smiley face for telling us time information at this end. The clock at this end doesn't really work, but this guy down at the bottom end understands more about where it's come from in terms of its family. All right, so another scale that I like to think about in terms of isotope geology and geochronology is the scale between a thermochronometer versus a geochronometer. So these are mineral, but also isotope scheme specific. So obviously we kind of know at the high temperature end, we've got zircon, uranium, lead, monazite, uranium, lead, garnet, SMND. These are all pretty high temperature systems telling us about the time through about 800 to 900 degrees. That obviously kind of equates to the crystallization age. We have mid-temperature systems that tell us maybe time through about 500 degrees. For example, a rubidium-strontium system in muscovite. Then biotite would be slightly lower again. So we can use these different schemes, different isotopes and different minerals to build up this thermal pathway through the crust of our rock. We can also get to low temperature systems, and a good example of that is apatite, uranium, thorium, helium, which tells us about 90 degrees C, the time through that temperature point. Okay, with that kind of introduction in mind, just very briefly, the general approach that we take at Curtin is a mineralogy-based or petrology-based approach where we like to maintain the petrographic context of our analyses. This helps on multiple fronts. It enables us to date different textures within the rock, but it also enables us to understand diffusional systems, so we can understand if systems are being reset or they're providing information about their primary growth age. So we tend to work either directly on thin section or on polished rock blocks, although we can work with mineral separates. And we tend to scan material using the TEMA or other imaging techniques to provide this context that we're interested in. The next step is usually a beam-based approach, depending on the spatial resolution we require. So obviously we've got the shrimp with that fantastic spatial resolution at the top, but also coming maybe with a higher speed of analysis, but also allowing us to do some more potentially challenging isotopes with interferences. We can use various laser ablation approaches, and I'll talk about this in a little bit more detail in the case studies. Just very briefly, we have a range of different laser ablation systems. We have a normal quadrupole setup, which is fast, great for rapid trace element analysis and potentially uranium lead. We have a quadrupole system with a triple quad and a collision cell attached. I'll touch on that in more detail. So this is where maybe some of the advances are coming, enable us to do some more non-standard geochronology. And then we've got high precision instruments with multi-collectors. So we're able to measure multiple isotopic masses simultaneously. And this is really a workhorse for lutetium hafnium. In zircon, it's widely used by the survey, but also it's important for lead, common lead isotopes. Okay, so that's the intro. So what I thought would be kind of fun is to go around the rock cycle and look at where we can use isotopic information to tell us about all these different processes. So let's start off looking at source. So source, basically the source fluid that's going to form a magma, where our magma is coming from. That helps us understand about the evolution of blocks of crust, where maybe there's major breaks and gradients between different crustal blocks. Okay, so you guys are familiar, obviously, with neodymium and hafnium, and that's been widely used in this space to understand different crustal blocks, and the survey has been at the fore of that, creating isotopic maps that help us understand, for example, the structure of the Yilgarn. We can do a similar sort of thing using lead isotopes in feldspar, but it maybe tells us more about the fractionation process in the mid to upper crust, rather than a deep crustal process that's probably being recorded by the fractionation system in neodymium and hafnium. So how does this system work? Well, we're not looking at radioactive decay within the K-feldspar itself. We're looking at the process or the signal that's being imparted from the source. So the fluid that's growing our feldspar, that's what we're looking at, the lead isotopic signature being set up. So our lead isotopes here, you can see there's 4 of them. 3 of these are produced from the radioactive decay of various uranium and thorium isotopes. So if our feldspar traps this lead signature, it's trapping that and it's not changing through time, because the feldspar itself doesn't have any uranium or thorium, so these signals are not being changed in the feldspar. So it's taking a snapshot and retaining that snapshot of the amount of uranium and the amount of thorium in that source fluid that grew the feldspar. The neat thing about feldspar is it's kind of ubiquitous in felsic crust, and lead rapidly or readily fits within its structure. So normally we have sufficient lead concentrations in about 70 to 80% of K-feldspar to actually make a meaningful measurement. The structure of K-feldspar, as I said, excludes uranium, which is kind of important because we're using this not as a clock, but as an isotope tracer. So the way this system works, on the diagram on the right-hand side, we're plotting the 6:4 ratio against the 7:4 ratio, and there are evolution curves that describe how a parcel of rock would be expected to change over time with an amount of uranium within it. So if we take, for example, 2 parcels of rock that are the same age but have different uranium contents in the source, they will plot along 2 different curves. These curves are described as a function of mu. Mu reflects the amount of uranium. So we can have a lower uranium source, which would be a mantle signature, but we can also have a higher uranium source, which would be a more crustal signature. And indeed, we could have an even higher, more fractionated signal from another crustal source that would plot higher up. But they plot along a isochron, which determines their age and shows that they're the same age. So where we lie along this age tells us about the uranium in the source. And this is pretty useful because what we can do now is we can go across our terrains, look at the K-feldspar, and map out the source signature to tell us how fractionated that source was. Has it come from evolved crustal material, or has it come from more mantle material, depending on the mu value? Okay, so what we've got here is a data set that we've collected in the middle here from K-feldspar. It's in progress, but we're basically mapping our lead isotopic signature from K-feldspar, and we're doing a little bit of maths with that to calculate a source age, very much like you would calculate a model age from neodymium or hafnium that the survey has been widely using to produce these beautiful isotope maps. The calculation process here is a little bit involved, but I'm happy to talk people through it. It's quite novel, but it does appear to be pretty powerful. What we can see is that there's broadly, with the data set as it currently stands, a similar sort of pattern between at least the eastern goldfields and into the you and me terrain, resolving some sort of structure here where we have less evolved crust in the eastern goldfields, versus more evolved crust on the other side. You can see the model ages are actually broadly similar between these two different systems. This is actually important because what it's telling us is that the deep crustal system was in communication with a much shallower crustal system in terms of its fractionation processes, pointing to the fact that the eastern goldfields may not be allochthonous, it may be an autochthonous system. What's interesting as well is that I would say that the K-feldspar map seems to show probably more similarity to the upper mantle S-wave velocity. So we are imaging probably slightly different depths of crustal signature between these two different isotope schemes, although the broad scale first order patterns do appear to be similar. On the right hand side, we've tried to do something a little bit different here. The Shannon-Weaver diversity index is a diversity index set up to actually understand biological populations, so how much variation there is in a pond, for example. So if there's a wide range of different values or different species within a pond, you'll have a high diversity index. If you've only got frogs in your pond, you're not going to have a large diversity index. Well, we can use the same thing for our lead isotope parameters. These lead isotope parameters are mu, which tells us about uranium, omega, which tells us about thorium, and kappa, which is the ratio between the two of these. So if we look at various sampling media, including our granite K-feldspar that we've mapped out, there's some interesting patterns. There seems to be more diversity in our evolved older crust, whereas our more juvenile eastern goldfields seems to have less diversity. And that pattern is repeated across the ores, the granite K-feldspar, but also the komatiite hosted material. And this is kind of consistent with the idea that the eastern goldfields is a more juvenile package. What's interesting, though, is that gold ores over everything show the greatest diversity. And this points to gold ores forming from a range of fluid sources, including both crustal and mantle fluids. Okay, so that's a very high-level overview of lead isotopes and how we can use it for crustal evolution. The lead isotope data that's being collected in partnership with the survey is also very important for carrying out or producing models that are fundamental to correct common lead in geochronology. So it's this underpinning technique. It's also useful for provenance analysis. I don't really have time to touch on those in any more detail, but I would be happy if anyone's interested to talk about that at a later point. Okay, so let's move on. Let's talk now about some new techniques and how we can gain more information about other igneous processes and the timing and time temperature pathway of igneous rocks. So while zircon is great, it's really a signature from a more felsic crust. So we can see this on the diagram here on the right-hand side, where we've got whole rock silica plotted against ppm zirconium. So it kind of peaks out around 65 to 70%. So zircons generally are telling us about a record of evolved crust. Now, through time, we know that there's periods of time that were dominated by felsic crust, but also periods of time where more mafic crust dominated. So if we're just looking at the zircon record, there's a real potential that we might be looking at a very biased record. So biased periods of time when we have more felsic continental crust being produced or dominating. So those periods potentially of supercontinental breakup, or other periods of time when more mafic rock demonstrates that might not be as well accounted for using the zircon record alone. What we can do is we can bring in apatite to help us here. So what we're plotting here is silica against phosphorus. Phosphorus is a useful indicator of apatite. Apatite's the main phosphorus mineral. And what you can see is apatite will tend to form in more mafic rocks. So looking at both zircon and apatite is going to enable us to understand the evolution of a parcel of crust, probably better than just looking at zircon alone, because we'll be able to get a signet from the more mafic components as well. All right, so what I wanted to do is give an example of that from Greenland. So we're going to go off to the west side of Greenland, some spectacular TTG rocks in the east coast of Greenland. It's an interesting area to to carry out field work in. Boat work is great. Flying around is not so good because of the mist. But I just want to point out that on this map, you notice that the area is highlighted as an area of low Proterozoic strain, and this will become important when we actually look at the data. So the traditional model for this region is that it records probably some of the best evidence for early Earth horizontal tectonics, and that's based on the idea that there is very little Proterozoic deformation in this area. The terrain itself reflects probably one of the largest, at least in the Northern Hemisphere, exposures of TTG. And we see an old dioritic component at about 3.2 GA. Most of the rocks themselves are about 3 GA. And there's multiple periods of high grade, and I mean upper amphibolite to granulite facies metamorphism that have overprinted this area. So that's the background of information. I should highlight that most of this, if not all of this information, is really based on zircon uranium-lead geochronology. Another interesting point is that the area has been proposed by Gaius and Adam Gard in particular as hosting what's known as the Minitsok structure, which has been proposed as the oldest impact structure on the planet. Based on some geochronology, zircon geochronology that was done, and also on the geophysical image, although I would kind of defy anyone to spot a circular feature in that, although that's what's being proposed. The work was published in quite high-profile papers in Earth and Planetary Science Letters and in Precambrian Research, but it's actually really important for the Society of Greenland because there's a norite belt that surrounds the proposed impact structure, and that norite belt, the exploration model that's being used in the area is a Sudbury-style impact genesis model for the nickel copper mineralization, which is some of the best shows of nickel copper in Greenland. So actually understanding the geology here has real implications for the mineral systems, and also trying to get to the bottom of, is this really an impact structure or not? Because it makes a big difference to how you interpret the regional geology here. So to add to the really good zircon database of ages, we can add apatite. Apatite uranium-lead geochronology. It's not like zircon. It's kind of one of these minerals that's halfway between a geochronometer and containing source information. In other words, it contains some common lead to large amounts of common lead. So that's lead that's basically trapped in the crystal at its initial growth. And that lead obviously has to be stripped out of our calculation of age because it would mess up our calculation. So what we see here are these linear arrays through the data where the upper part of the data points to the common lead component. So we can see this analysis had pretty much 100% common lead. Our apatite down at the bottom end, which tends to be apatite with higher uranium content, preserves more of the radiogenic, therefore the time information, and we get a mixing line between those components. We also have other complexity in the data set because apatite closes at about 450 degrees C. So depending on the grain size of the apatite, it might have gone through its blocking temperature at a different, at slightly different times. So we can get an array of ages. You'll see at the end that we're actually able to make quite a lot of sense out of this spread of data. But to really enhance the information, we decided to look at what's a few other systems in apatite. So we also looked at samarium neodymium in the apatite. Samarium neodymium in apatite has got a much higher closure temperature than the uranium lead system, and that's pretty important because now we're getting 2 points on our time temperature pathway. It's an isochron technique, so we also get information about source fluid that's that our apatite is growing or recrystallizing in. Obviously, the precision is not the same as the precision of a uranium lead technique, but regionally, if we have enough analyses, I think we can draw quite firm geological conclusions from this sort of data. We also have attempted lutetium hafnium in apatite. Lutetium hafnium in apatite is a brand new technique, and it's made possible by the collision cell instrumentation. We show these on what's known as inverse isochron diagrams. Apatite really likes lutetium, but it really doesn't like hafnium. So all the hafnium that is trapped in our apatite is pretty much from the radioactive decay. So it's very much like zircon and the way zircon loves uranium but hates lead. So it's actually a really good chronometer. That's why on these diagrams, they plot really low down on the hafnium axis around 0. So essentially, there is no common hafnium. All the signal is a signal from the radioactive decay of lutetium, which gives us ages. Analytically, I can talk about this in a little bit more detail, but spot size-wise, we're looking at spots of probably about 70 microns to do this sort of analysis. With the samarium neodymium system, we're looking at analytical spots of about 40 microns in size. The reason this is powerful as well is it opens up the possibility of actually getting ages out of more mafic components that we haven't previously been able to get ages out of. All right, so let's look at all this data together. So we have our zircon ages here from similar rocks or associated rocks. They are the age of our TTGs at about 3 GA, so they're in diamonds. The ages of our lutetium, hafnium, and samarium neodymium system are here. The lutetium hafnium system didn't really have any firm constraints on its closure temperature or its blocking temperature. But given its similarity to samarium neodymium and also the chemical similarity, we expect the closure temperature to be roughly similar, so that around 800 degrees C. There's obviously a pair of outlier analyses, and I'll talk about those in a little bit. The histogram at the bottom is a histogram of the uranium-lead apatite ages. So what we see is large apatite ages have similar 3 GA ages to the crystallization of the TTG, but there's a pattern reflecting diffusion and recrystallization of the grains, and a really strong signal of recrystallization during a 1.7 GA event, which correlates with the Nastikidian orogeny. And that's really interesting because previously the front of the Nastikidian was 200 kilometers further north. So there seems to be quite a profound effect of this Proterozoic event in a region that was only really thought to have Archean processes. That's pretty important. The other important point is that the impact event was supposed to occur at 3 GA. The difficulty with that is we now have a granulite facies event that caused widespread melting and also isoclinal folding just after that event. So how you could preserve an impact structure through a granulite facies event seems rather improbable. So I don't think a impact genesis really works for the Minitzoq structure. Fitting all this information together along with information from rutile and titanite, and information from pseudosections, we can actually build quite a detailed numerical model for the thermal pathway of these rocks, and that's probably the end goal of this type of geochronology and thermochronology. Just to really reiterate that we don't think an impact structure works. Imaging is also really useful, so we can do EBSD, so that's electron backscatter diffraction, to look at the internal structure of our zircon grains. And what we see is on the right-hand side our TTG zircon from Greenland looks pretty normal. It's nicely crystalline, other than highly metamic core regions. We see no impact structures. So on the right-hand side, we've got classic impact structures from Western Australia. There are planar shock twins standing out in red here. We see none of that in Greenland. And also beautiful polycrystalline textures where zircon is recrystallized due to an impact process. Looking at approximately 6,000 zircon grains using this technique, we've been able to do that because of new instrumentation at Curtin that has faster scanning rates, including younger sediments. So potentially you could argue that the rocks have just gone from the impact, but we looked at younger sediments. We also looked at magmatic rocks directly from ground zero, and we don't see any shock textures. So I think the impact hypothesis doesn't work, and that probably has implications for the style of mineral system, or at least the mineral exploration model that's being applied. Finally, just on this, it's kind of interesting to think about the implications for Proterozoic deformation in the area. This area, as I said, has been considered as kind of the prime example of horizontal Archean tectonics with arc accretions and subduction zones. I would point out that there is widespread Proterozoic mineral growth seen in apatite, titan, and biotite that probably hasn't been fully recognized before because of the interest in using the more high temperature systems. So the question really is, are the horizontal tectonic features that are being proposed from here, are they really good evidence of processes in the Archean, or are they just a reflection of some of the profound overprinting that we think has happened in this area? Okay, that's a little trip to Greenland. Hopefully that was enjoyable. Some nice pictures of rocks. I'd like to talk now about is more computational style tools that we've developed at Curtin to look at sediments and sedimentary rocks. There's only going to be one slide, but I think it's quite a useful observation. So relatively recently, Kaywood, Hawksworth, and Dweem published in Geology quite, well, it was a very useful paper, I think, where they pointed out quite a simple observation. That observation is kind of demonstrated on the right-hand side here. If we've got a detrital zircon spectra, so this is the ages of detritus, and we know the depositional age, there seems to be a relationship between active margins where you have more detritus that's similar in age to the depositional age. So you have volcanic material, let's say, that's close in age to the depositional age. Whereas a passive margin, there seems to be a larger time gap. So that's kind of useful. But the problem with that, in terms of applying it through the deep time rock record, is that, well, especially in Western Australia, we don't have great depositional age constraints on some of our sediments. So we might have fantastic detrital zircon spectra that are quite detailed and quite precise, but we don't know the depositional age. So using this to tell if you've got an active margin or if a passive margin becomes quite challenging. Potentially there's something else we can do though. What we've noticed using a massive database of pretty much all published detrital zircon spectra is that there appears to be a correlation between the complexity of the detrital zircon spectra and its tectonic setting. So again, it's noticing that in active margins or collisional settings, you seem to have a more simple spectra dominated by a single dominant age peak, whereas in divergent or passive margin systems, we seem to have a more diverse age spectra. So we can come up for we can develop metrics for that, looking at the difference between the 10th and the 50th percentile of this age signature and comparing it to the chi-squared metric. So we can use statistical metrics to basically quantify whether we're in a passive or an active margin, and it works to greater than 95% confidence. So we're quite pleased with this tool. An example of this from more modern systems is a system from South America, going from the Andes right away across down the Amazon River, and it classifies really pretty well the different settings. The few analyses that don't classify well in the Andes actually reflect samples where there has been more reworking. But it seems to work really well classifying the difference between active margins and passive margins, and we've applied this back through time, and it seems to hold true at least as far as the Proterozoic is concerned. Okay, getting there. We've nearly got all the way around. Talking about metamorphic processes now, and we'll look at rubidium strontium to try and understand metamorphic rock fabrics. The reason that we can only do this now in terms of an in situ technique, traditionally this was approached through laborious mineral separation, but also column chromatography to separate out the elements of interest to actually put through a TIMS mass spectrometer. The reason that we can now do it in situ is through the development of what's known as triple quad instruments. Triple quad instruments contain 2 quadrupoles with a reaction cell in between. Unfortunately, this diagram is going from right to left, whereas the instrument here is left to right. But basically, what I want to show is where the gas comes in, it reacts in the collision cell. The collision cell, we use nitrous oxide, so laughing gas. Basically, we use the laughing gas to collide out unwanted species. So we're left with the strontium that we want to measure. We then use the quadrupole to have an energy barrier to stop these other collided out ions passing through, and then we pass it to the detector. The challenge basically here is we need a high precision instrument because 87 strontium and 86 strontium, the 2 things that we're interested in that tell us about time, are not the most abundant isotopes. So we need a good collection system at the end of the instrument. We also need to deal with this interference of rubidium because rubidium is sitting on top of the 87 that we're actually interested in measuring. That's why we want to use this collision cell to collide out this interference. In a little more detail, what we can see in the cartoons here is that a simple reaction cell does a pretty good job in colliding out most things that we're not interested in. But you can note the peak here is stacked up. So there is other things interfering. So our strontium here is not too happy. Actually, to be fair, I don't know why he's not too happy. He's just passed through a lot of laughing gas. But the double focusing, or the instrument, which has an extra quadrupole at the start, enables us to already do a mass filter at the front. So we've got less of the competing species passing through. So it's all about carrying out essentially column chemistry that would take weeks within the instrument itself to get a clean signal. All right, so let's have a West Australian example from this very briefly. I know you guys are familiar with the Albany-Fraser origin and the Tropicana zone. Tropicana zone is obviously important because of the Tropicana gold deposit reflecting reworked Archean Yilgarn margin. The time-space diagram kind of highlights we've got early granulite facies metamorphism. We also have emplacement of magnesium-rich granites, so mafic granites, sinukitoid style, which might have been the original source of the gold. And we have a range of other overprinting Proterozoic events, including Albany-Fraser stage 1 and stage 2. The original work by Mark Doyle, based on rutile and also argon work, pointed and some rhenium osmium, all kind of gave ages broadly around 2530 for an assemblage associated with gold. Part of the issue with this age is that we know the area has gone through granulite facies metamorphism just previous to that. And the question here is really, is this assemblage that's been dated through these different techniques, does it reflect the time of crystallization of this assemblage, or does it reflect cooling? What we wanted to do is try and test that in a little bit more detail. So we went and we looked at some biotite fabrics. What I'm pointing out here on this time-space diagram here is this progressive suggestion of maybe granulite to green schist facies, with the ages here being the ages proposed for major mineralization within the Tropicana deposit. The biotite forms 2 different assemblages, with both assemblages associated directly with gold. The in situ technique that we use allows us to place a 20 to 30 micron spot within biotite of both these generations and try to determine its blocking age, or potentially its crystallization age, depending on the thermal history of the rock. The data is presented on isochron diagrams, and we can tie the bottom end of the isochron diagram with petrogenetically coeval apatite. So what we can see is we get a older assemblage of biotite with this 2530 age matching the ages of Doyle from older, texturally older biotite, which has in X solution of titanite. We also have from biotite 2, which is a later generation of biotite, a younger isochron, an age of about 1200, which matches Albany Fraser stage 2. We also, along a similar shear zone slightly further south, we sampled material rutile associated with a mineralized zone. And that rutile has high tungsten, so it's compositionally different to normal rutile in the area, and it also yields this Albany Fraser stage 2 age. The implication is that there is gold mineralization associated with AFO stage 2, and that's probably quite important given that we know that the stage 2 event was a widespread fluid event across the entire origin, forming overgrowths on essentially all zircon populations. All right, last case study, for the people still hanging with me. What we're going to do is look at low temperature processes now. Again, we're going to go to West Greenland. Now, this has kind of implications as well for Australia because West Greenland is actually quite similar in terms of its very old rocks with a much younger history of rifting with an elevated planation surface. The idea of an elevated planation surface actually has raised quite a lot of questions around the geomorphology community. So we can see on the cross sections here, these elevated planation surfaces and what might they reflect. So we went and we looked at uranium, thorium, helium in apatite and zircon. So apatite helium is telling us about time through 75 degrees C, whereas zircon is telling us about time through 180 degrees C. The way this works is it's a bit more of a laborious process. We pick individual grains, we put them into steel capsules. The capsule is closed, and it's another laser technique where we heat the capsule to release the gas. We also measure the uranium, thorium, and samarium simultaneously, which is needed to calculate these ages. The ages from different samples are shown on a map on the left-hand side here, and also on these kind of contour maps on the right-hand side. Zircon is interesting because it yields very old ages, some of the oldest helium ages that have ever been recorded, and that speaks simply to the stability of this part of the craton. However, the helium shows a younging path towards the coastline. That younging path is consistent with the breakup of Greenland from Canada and the development of the Labrador Basin. Now, this is actually quite interesting if we look at the timing of this. In blue is our apatite helium ages, and also compared to some other geological records from the area, including the magmatic dike record, also fluvial sediments, the age of fluvial sediments, and the age of full marine sediments. What's interesting is this rifting between Greenland and Canada appears to coincide with what's known as the Aptian oceanic anoxic event. So generally in the Cretaceous, we think as a global hothouse, greenhouse conditions were dominating, but within those greenhouse conditions, there were episodic events of quite profound cooling. The Aptian event itself has been associated with the large igneous provinces and release of CO2 causing a global catastrophe in carbon sequestration, with organic matter being formed and dropping out. But within that process, there appears to be these quite distinct drops in the strontium isotopic record, which speaks to periods when there was very little rainfall. The easiest way to account for that are cooling phases. So we had episodes of profound cooling in the entire North Atlantic region. One way to potentially do that is through stalling the North Atlantic drift. So that's the thermohaline circulation system that carries heat northwards. So I guess you guys may recall the 2014 speculative flick, The Day After Tomorrow, for both its kind of insane action sequences and probably gross inaccuracy in some of its science. But more recent climate modeling has pointed out that if you stall this conveyor belt, you would indeed cool temperatures in the North Atlantic by 8 degrees C and result in potentially a northern hemisphere cooling entirely by about 3 degrees C. What's important is this northward current of warm water becomes very salty and drops on the east of Greenland to become a deep circulation current. That deep circulation current falls in two places particularly. One is here, but there is also a second major overturning of seawater here in the Labrador Sea. If we think about the kind of Cretaceous paleogeography and the development of the Labrador Basin at this time, as determined from our uranium, thorium, helium ages, we think that opening a basin at this time potentially would have significantly modified this overturning circulation cell by influx of large amounts of fresh water, potentially shutting down this thermohaline circulation cell. Okay, so that's basically everything I wanted to cover with a few case studies. I hope you find it interesting, just showing the diversity of ways that we can use isotope geology to tell us about low temperature and high temperature processes.